Welcome to the video on carboxylic acids and derivatives. In this video, we will talk about carboxylic acid, their physical properties, how we name them, and specifically the acidity of carboxylic acids. So as we introduce carboxylic acids, they're everywhere in nature. Acetic acid is vinegar, and that's what that looks like. And acetylsalicylic acid, that's aspirin. So when we get a headache, we take that. Here's another drug used for tuberculosis. Here's lactic acid. That's the one that builds up in our muscles when we have muscle aches and pains, and it's also responsible for the sour taste in milk. So carboxylic acids are everywhere. So when we name carboxylic acids, we're going to use the same rules that we've used for alkanes and alcohols. We're going to find the longest carbon chain. We're going to look at substituents. We're going to talk about where the substituents are. In order to get the ending of the name, we're going to figure out which functional group is in the molecule and which functional group wins. Well, it turns out that carboxylic acids win. They are the ultimate winner of nomenclature. So if there is a carboxylic acid in the molecule, then the ending of the word will include oic acid as shown here. And so this simple example right here, we have a carbon chain that is 4, so that's bute, so that would be butanoic acid. Perfect. So now this one here is a little bit more complicated. So you see that we have our longest carbon chain is 1, 2, 3, 4, 5. The longest carbon chain has to include the carboxylic acid, and the carboxylic acid is always going to get carbon number 1. So here's 1, 2, 3, 4, 5. And what we have on carbon number 5 is this OH group. It doesn't get the ending of the name. So remember, when we have an OH, we're going to call it a hydroxyl. So this is going to be 5-hydroxy. And then we also have the substituents here and here. So this is going to be 4,4-dimethyl. And then our longest carbon chain is pent. So if we put that all together, we should have 5-hydroxy 4,4-dimethyl pentanoic acid. The reason that hydroxy comes before the methyl groups is because we don't count di and tri in our alphabetical order. We're going to go to the M. So it would be 5-hydroxy 4,4-dimethyl pentanoic acid. So carboxylic acids get the ending of the word no matter what. Oic acid, they always get carbon number 1. They always have to be at the end of the chain, so they're always going to be on carbon 1. And then everything else is exactly how we've learned it with other molecules. If the carboxylic acid is a substituent and the carbon of the carboxylic acid is actually not on the parent chain, it's off. So if we have a carboxylic acid that is a substituent, then what we're going to use is the ending to the molecule carboxylic acid. So this case right here would be cyclohexane carboxylic acid. The way that you can remember this is the word is going to be oic acid if the carbon is already counted in your parent chain. If the carbon that's on your carboxylic acid is not already included in your parent name, like this example, then we're going to use carboxylic acid as the ending. Here's a few common names of carboxylic acids. We have formic acid, which is the simplest carboxylic acid with only 1 carbon. Acetic acid, again, vinegar. Propanoic acid, butyric acid, and benzoic acid. Benzoic acid is benzene with a carboxylic acid substituent. We also have examples of dicarboxylic acids. In other words, we have 2 carboxylic acids in the same molecule. This is not something that you have to know necessarily for the test, but I would like you to just be aware that they exist. The way we name them is pentane dioic acid. And then here's some common names. And some of these are ones that you may have heard of: oxalic acid, malonic acid, succinic acid, and glutaric acid. Some of these you may recognize from the citric acid cycle. So if we talk about the structure and properties of carboxylic acids, the first thing I want you to know is that the compound is planar. Remember that carbon right there is sp2 hybridized. And so it is a flat molecule with bond angles of about 120 degrees. So it has trigonal planar geometry. Secondly, because of the OH group on a carboxylic acid, we end up forming this intermolecular interaction between two molecules of a carboxylic acid. The OH hydrogen bonds with the carbonyl oxygen of the other molecule here, and that's a strong interaction. Also, we have the OH of the second molecule hydrogen bonding with the carbonyl oxygen of the other. It's called a cyclic dimer, and that's where we have these two hydrogen bonding interactions between two molecules of a carboxylic acid. And this does make the boiling point higher for carboxylic acids because of the increased intermolecular interactions of those hydrogen bonds. Now, if we talk about the acidity of carboxylic acids, we probably do remember, considering it's in the name, that carboxylic acids are acidic. And so what happens is we have a base reacting with our carboxylic acid. The lone pair from the oxygen reaches out and forms a new bond with the hydrogen. And then the two electrons in this bond hop onto the oxygen, creating what's called our carboxylate salt, or simply our conjugate base. If we were to name the conjugate base, that charged species, we are going to use O8 in the name instead of oic acid. So if this compound right here is benzoic acid, then it's going to be sodium, because that's our counter ion, benzoate. You will not be responsible for naming the carboxylic acid's conjugate base or these carboxylate salts in this course for me. So if we look at a carboxylic acid in water, so again, we don't have that strong base, but we just have a base, we can do the same reaction. So we're going to do a proton transfer, and then those electrons will hop back up onto the oxygen there. So we end up forming the conjugate base here in the conjugate acid. If we look at some representative pKa's, we have a pKa of 4.19 if we have a benzene ring. We have a pKa of 4.76 if that's just a methyl group. And if we have an ethyl group, it's similar at 4.87. Now, if we compare that pKa to that of the pKa of an alcohol, the alcohols have a pKa of 16, whereas carboxylic acid, acetic acid specifically, has the pKa of 4.76. So why the difference? And I hope that you remember using ARIO, right, the resonance. So when we form the conjugate base of this acid right here, we get this species right here. We can take those electrons, kick in to form a double bond. This double bond breaks. Those two electrons hop up onto the oxygen. So we have the resonance structure shown here. And anytime a compound can have resonance, it is more stable. So the carboxylic acid here, circled in green, is a stronger acid because its conjugate base is more stable because of resonance. And that's the R in ARIO. Carboxylic acids are stronger acids than alcohols because their conjugate base is stabilized by resonance. And hopefully that's review for you. If we take it a little step further, and instead of just referring to the resonance part of ARIO, and we take a look at the inductive effect, we can actually affect the pKa's of a carboxylic acid by adding electron withdrawing groups to the carbon. Here is a simple carboxylic acid without any inductive effect. This one, again, still has resonance, so it's still a stronger acid than an alcohol. But as we add chlorines to our carbon here, these chlorines are going to be electron withdrawing, so they're going to pull electron density away from the developing negative charge on that oxygen of the conjugate base. So as we add chlorines, one chlorine, we see the pKa go down to 2.9, two chlorines, it goes down to 1.3, and three chlorines, it goes below 1. And so as we add these electron withdrawing groups to the carboxylic acid, we see that inductively, the conjugate base is more stable. So another way that we can say that is as we add electronegative and electron withdrawing groups to the compound, we can make a stronger acid because the conjugate base of this acid right here is more stable, not just because of resonance, because they both actually have resonance, but because of the inductive effect. So the electron withdrawing group is inductively stabilizing the conjugate base. And distance does matter. If we have those chlorines on the alpha carbon, we see that the pKa is 2.9. If we have that chlorine on the beta carbon, we see that it's 4.1. And if it's on the gamma carbon, we see that it is 4.5. So as the electron withdrawing group, as the inductive effect goes away from the developing negative charge of the conjugate base, in distance, our pKa goes back up and we have weaker acids. Okay, so I hope that helps. A little bit of insight into carboxylic acids as we delve into the last chapter of the semester. Good luck.